The virtual work method can also be used to predict deflection of beams. And this problem will predict displacement of a beam at a particular point using the virtual work method. And the key concepts we'll use are selecting the appropriate virtual load for predicting a particular real deflection and generating equations for moment in a beam. And here's our beam. It is simply supported, pin at A, roller at B, with a cantilevered end out to C, with a uniform distributed load from B to C, and we want to predict the vertical displacement of C. So we'll identify a coordinate system, and what we're looking for is delta CY. It's a steel beam, which means that the modulus of elasticity is 200 gigapascals, and the moment of inertia is 70 times 10 to the 6th millimeters to the 4th. And now our approach. In most of our examples, we've created an approximation of the solution that we use to compare to our more lengthy calculation at the end. That is one approach to making sure we have a reasonable result. Another approach is to calculate the quantity using two different methods. And so in this case, we're going to start by predicting the vertical deflection at C, and we're going to use formulas from the front cover of our textbook. Then we'll move on to the virtual work method, so we'll need to get the moment equations for the beam due to the real loads, and then the moment equations from the virtual load. We'll then be able to predict the vertical deflection at C using virtual work. And then our last step is to compare the predictions. If they don't match, we'll have to go back and evaluate why. We can't always predict deflections by formulas from the front of the book. But in this case, if we're a little bit creative, we can find a way, because this geometry doesn't match exactly. Let's start by sketching out the deflected shape we expect, or the elastic curve. We have a hump between A and B, and then downward slope from B to C. But we call B to C the cantilevered end. So let's see if we can create a superposition to help figure out our deflection at C. If I take just the left piece of the beam, that cantilevered end causes a downward couple moment on the left piece, which gives me the arched displaced shape we see above. And at this end, if we extend the tangent and the horizontal, we have a rotation theta And a deflection out at end C of this extended tangent we'll call delta 1. Now if we add to this, the cantilevered end already rotated by an angle theta, we have the uniform distributed load acting normal to it, that causes a deflection. We'll call delta 2. Now we can calculate the normal displacement using formulas from the front cover of the book. And as long as our actual deformations are relatively small, this displacement and this displacement are identical. Now, do we have a simply supported beam with a couple moment applied at the end? So as we take a look inside the front cover, we have prediction for deflection for a cantilever uniformly loaded, and we have a simply supported member with a couple moment, and prediction of the slope or rotation at the end. The L refers to the left end, and so this quantity is the slope at the end where we apply the couple moment. Now if these formulas are too small to see, that's okay. Refer back to your textbook, but I'll write them down as we need them. First, let's find out what that moment is holding the cantilevered end. So that end is 5 meters long. The uniform distributed load is 2 kilonewtons per meter. And let's draw our moment reaction, or the internal moment at point B, in the counterclockwise direction. I'll sum moments about point B. I'll take counterclockwise as positive. We have the internal moment at B, and we have in the opposite direction 2 kilonewton per meter over 5 meters gives me the total force, and it's at a distance of 5 over 2 meters from point B. So the internal moment at B is a plus 25 kilonewton meters, and we drew it as positive on this side of the cut, which would mean it's positive clockwise on the other side of the cut. So now let's use that formula for slope at the end of a simply supported member with a couple moment applied, and it's the couple moment times the length of the member over 3 EI. And in this case, that's a minus 25 kilonewton meters, because our formula is based on a couple moment going clockwise. In this case, our couple moment acting on member AB is going clockwise. Oh, so the original was drawn going counterclockwise, this one goes clockwise, so it's a negative quantity. AB is 10 meters long. We divide by 3. 200 gigapascals is going to be 200 times 10 to the 6th kilonewtons per meter squared. And so our kilonewtons will cancel numerator and denominator. And my cross-sectional area, 70 times 10 to the 6th, not cross-sectional area, moment of inertia, millimeters to the fourth. And my units are not consistent. I get meters to the fourth in the numerator and millimeters in the denominator, so I will convert to get consistent units, and I have 1,000 millimeters per meter raised to the fourth. All that together gives me a slope at end B of negative 5.95 times 10 to the minus third radians. But because we're talking about small deflections, that slope is also the rise over run. So it's also delta 1 over 5 meters, which I can shuffle around and find that delta 1 is a minus 5.95 times 10 to the minus third times 5 meters, or 5,000 millimeters. So that is a minus 29.8 millimeters. Now delta 2, the normal deflection of a cantilever under uniform distributed load. And the formula of the inside of our book reads a minus the distributed load times the length of the cantilever to the fourth over 8 EI. So that equals a minus 2 kilonewtons per meter times the 5 meter cantilever length raised to the fourth over 8 times the 200 gigapascals, which is 200 times 10 to the sixth kilonewton per meter squared, and our moment of inertia, 70 times 10 to the sixth millimeter to the fourth. And so now I have meters to the sixth divided by meters, meters to the fifth over millimeters to the fourth. Let's convert all to millimeters. So I have 1,000 millimeters per meter raised to the fifth. Put all of that together and I get a negative 11.2 millimeters for this component. So my prediction of the vertical deflection at C is the sum of these two, negative 29.8 millimeters minus 11.2 millimeters is a negative 41 millimeters, and our formulas are based upon up as a positive quantity, so it's predicted down. Now step 2. Moment equations for the moments induced by the real load. We will need two equations to describe moment along the entire beam. Origin and direction of each x is my choice. To simplify the expressions for moment, I'll set the origins where the moment is 0. So I'll have x1 starting at A and moving to the right. I'll have x2 starting at C and moving to the left. So let's find the reactions. A vertical reaction at A, vertical reaction at B, and a horizontal reaction at A. Let's sum moments about point B. I can choose clockwise or counterclockwise as positive for my summation, and I'll choose clockwise because all of the components are causing a clockwise rotation about point B. We have the 2 kilonewtons per meter distributed load acting over 5 meters, which gives us the total force acting at a distance of 5 meters over 2 from point B. So I find that AY is a negative 2.5 kilonewtons. Up would have been positive. Now I sum forces in the Y. Choose up as positive. I have the negative reaction at A, the assumed upward reaction at B, and the downward distributed load acting over 5 meters. So BY is a positive 12.5 kilonewtons. And it is up. I'm now ready to cut it somewhere between A and B in the range of x1, and I'll keep the left side of the piece, so it'll have a length of x1. Vertical reaction at A of minus 2.5 kilonewtons, a shear unknown at the cut, which is a function of x1, and a moment at the cut, which is an unknown function of x1 also. So now we'll sum moments at the cut. This time I'll choose counterclockwise as positive, since the unknown moment is drawn counterclockwise. I get a negative rotation in the direction drawn, but a negative magnitude for our reaction at A through a distance of x1, and my unknown moment at the cut, M. Solve that, and I find that my moment equation is minus 2.5 kilonewtons times x1. Now we're ready to cut it somewhere in the range of BC, which is in the range of x2. We'll draw the right piece, which has a length of x2. We have the uniform applied load of 2 kilonewtons per meter. The unknown shear as a function of x2, and the unknown moment as a function of x2. Let's sum the moments about the cut. This time I'll consider clockwise rotation as positive, since my unknown moment is drawn clockwise. So I have my contribution from the unknown moment at x2 plus the effect of the 2 kilonewton per meter distributed load through a distance, or over a distance x2, gives me the total force at a location x2 over 2. So my moment as a function of position x2 is a minus 1 kilonewton per meter x2 squared. Now to repeat the step, to find the moment equations, due to the virtual load. Which means we'll have to take off the real load and apply the virtual unit load at point C. Because we want deflection at C, we'll apply it vertically because we want vertical deflection at C. I'm guessing that deflection will be down, so I'll draw it down. If it turns out I guessed the wrong direction and it's up, I'll get a negative quantity for my answer. Now I must still use the same axes for my moment equations due to the virtual load. Start by finding reactions. We'll have a vertical reaction at A that I'll call lowercase ay, since this is the virtual system. We'll have by and ax. At some moments about point B, I'll choose positive rotation to be clockwise, because all of the loads as drawn contribute in a positive or contribute in a clockwise direction, and I get ay is a negative 0.5. It's not in the direction drawn, which was up. Now some forces in the y direction. Take up as positive. I have the negative 0.5 reaction at A. By, which is assumed, is up, and the virtual load applied at C. Solve for by and I get a positive 1.5. It is in the direction I originally drew it. Now I'm ready to cut it somewhere between A and B and draw a free body diagram. Cut in the range of x1. I'll keep the left piece, which has a length of x1. The negative vertical reaction at A, an unknown shear at x1, and an unknown moment as a function of x1. I'll sum moments about the cut, and I'll take counterclockwise as positive. I get in the negative direction, but then a negative magnitude for the force at A through a distance of x1, and a positive moment as a function of x1. Solve that for my moment equation and get negative 0.5 x1. Now I can cut it between B and C, which is in the range of x2. I will keep the right piece this time, since it has a length of x2. We have the applied virtual load, unknown shear as a function of x2, and the unknown moment as a function of x2. So I sum moments about the cut. In this case, we'll take clockwise as positive. We get a positive contribution of the unknown moment, which is a function of x2. And we get a positive contribution from the virtual load, acting through distance x2. Solve that for my equation of moment in the range of x2, and I get a minus x2. We now have all the information we need to predict the vertical deflection at C by the virtual work method. That deflection is given as a summation of the integral for each piece, the moment due to the virtual load times the moment due to the real load over EI integrated over the length of the piece. So from A to B, it's 0 to 10 meters. We saw that our little m, our moment due to the virtual load, was negative 0.5 x1. The moment due to the real load was negative 2.5 kilonewtons times x1. We divide that by EI and integrate over dx1. Now for the other piece, B to C, we integrate from 0 to 5 meters. Our moment due to the virtual load was minus x2, and due to the real load, minus 1 kilonewton per meter times x2 squared. All of that divided by EI and integrated over x2. So we multiply these two quantities together and we'll get a polynomial that is a constant times x squared. So the negatives cancel out and I get a 1.25 kilonewton, and then the x1 squared gets raised to 1 higher power, x1 cubed, and then we divide 3EI, and this will be evaluated from 0 to 10 meters. Then we add from this component, the two negatives cancel, and we get 1 kilonewton per meter. We have x squared, so we have an x cubed that we integrate, so we raise it to 1 higher power, x2 to the 4th, and divide by that new exponent times EI, and we evaluate that from 0 to 5 meters. So if I start plugging those in, evaluating the integrals, we get 1.25 kilonewtons times 10 meters cubed over 3. E is 200 gigapascals, which is 200 times 10 to the 6th kilonewton per meter squared, times 70 times 10 to the 6th millimeters to the 4th. We have units of meters to the 5th in the numerator. The kilonewtons cancel. We have millimeters in the denominator. Let's be consistent and make everything millimeters. So we have 1,000 millimeters per meter raised to the 5th power. We subtract this expression evaluated at 0, and that'll give us 0. We add in this expression evaluated at 5 meters, so we have the 1 kilonewton per meter, 5 meters to the 4th, 4 times the 200 times 10 to the 6th kilonewton per meter squared, and the moment of inertia 70 times 10 to the 6th millimeters to the 4th, and we need consistent units, so we'll multiply by 1,000 millimeters per meter, again raised to the 5th power. And we'll evaluate this expression at 0, and that's a minus of 0. If I evaluate the first term, I get 29.8 millimeters. Subtract the 0, add the second term, I get 11.2 millimeters, and so it's a positive 41 millimeters. Remember, in this case, positive means down, because back when we applied our virtual load, we applied our virtual load down. So a positive deflection means it's in the direction of the virtual load. Now we're ready to compare the predictions. From virtual work, we have 41 millimeters down. Creatively using the formulas from the front of the book, we have a negative 41 millimeters up, which means 41 millimeters down. So our predictions are identical. That gives me pretty good reassurance that we have a reasonable prediction of the vertical deflection at C. Great job! Now let's go back and review the process we followed. Rather than starting with an approximation of the vertical deflection at C, we decided to use two different methods to predict vertical deflection at C and then compare their results in order to ensure we have a reasonable prediction. And for this particular geometry, it turns out that we can creatively, if we think creatively, we can use formulas in the front cover of our text to predict the deflection, and that's what we did. We used information for cantilever beams with uniform load and simply supported beams with a couple moment at the end. We then moved to virtual work, and we started by constructing or calculating the moment equations for the real load. We needed two equations, and since you get to pick the origin and direction of the axis for each equation, I tried to pick the origins that would make my equations as simple as possible, since we have to multiply them times other equations and then integrate them. And so I started where the moments would be 0. We have to keep the same coordinate axes for the moment equations for the virtual load. Then we combined them, integrated them, divided them by EI, and came to a prediction of vertical deflection that matched exactly with our prediction at the beginning based on formulas from the front of our textbook.